Here we are going to be differentiating between adding resistors in series and adding resistors in parallel versus the inclusion of both connections in one circuit. We are going to be looking at the relationship between resistance and current from the effects of parallel and series connection. This is the circuit in study whereby a question arises about the ammeter reading and the voltmeter reading when switch S is closed. We are mainly focused on the ammeter reading, which is affected by the resistance existing within the circuit. The misconception we are going to decipher arises from theory that in series connections, resistance increases as more resistors are added in series. In this scenario, they assume that one resistor being disconnected as switch S is opened. It implies the total resistance decreases, of which is incorrect. From the previous slide, according to the learners, resistance being inversely proportional to the current, it means that the resistance is decreasing and the current would increase. But in actual fact, resistance did not decrease. But first, let's check these practical models of similar cases.
Wasn't in series. And so the first thing that should stand out to you is that these two bulbs are as bright as that one bulb when it was before it was hooked up in series. And so another thing that's happening is that we actually have way more amps moving through this, and so you can see that the electrons are moving more quickly. And so the difference between a series circuit and a parallel circuit is that the current is actually increased. Remember when we had, let's go back and remove this and just connect it together. So remember here we had 0.9 amps for one light bulb, but here we now have 1.8 amps. In other words, the electricity is actually flowing faster. Why is that? Well, here there is the current of this thread and there's the current of this branch, and the two currents together are going to sum up to this this current. And so before, when we were saying the voltage drop in each of those sums up to the voltage of the battery, well, in a parallel circuit, those two pathways, in other words, those two currents, are going to sum up to the current of that whole the whole branch. Another thing that happens in a parallel circuit, let's kind of remove this light bulb. And so remember, when I removed a series light bulb, the whole thing went out. But in a parallel circuit, when I remove one of those light bulbs, the other one keeps moving. Now you should have seen that when I removed that light bulb, the amps dropped down to 0.9.
Here we are showing a more clear diagrammatic representation of a series connection of resistors and also a parallel connection of resistors. We assume that the light bulbs are our resistors. In a series connection, the total current decreases as more resistors are added in series. The resistance decreases as more resistors are added in parallel. Simultaneously, the above statement promotes total resistance of a series connection to increase, thus affecting the total current to decrease. In the next slide, we are going to look at the theory calculations of resistors in series and parallel and how we isolate parallel connection from a series connection. We are going to add values to the resistors to show how resistance changes in two cases by calculating the total resistance with switch S closed and then opened. First, we assume that the values 1, 2, and 3 are the ohm reading of the respective resistors. In case 1 of a parallel connection whereby switch S is closed, the total resistance RT is equal to R plus Rp. The general formula for calculating the parallel connection resistance Rp is equals to the product of R1 and R2 divided by the sum of R1 and R2. Substituting the values of R1 and R2 on the parallel connection formula, we substitute R1 by 2 and R2 by 3, which gives us the answer of 1.2 ohms, which is the overall resistance of the resistors connected in parallel. Now, calculating the total resistance, we take resistance of 1 ohm plus the resistance of the parallel connection of 1.2 ohms, which gives us the total resistance of the circuit as 2.2 ohms. This is the resistance of the circuit when switch S is closed. In case 2 of our scenario, the total resistance is equal to R1 plus R2, which is 1 ohm plus 2 ohms. This gives us the answer of 3 ohms. Now comparing this to the total resistance of a circuit whereby parallel connection existed, we can see that the resistance has increased. Now with the resistance being inversely proportional to our current, it means opening the switch, the total resistance has increased, thus the current has decreased. In conclusion, the ammeter reading decreases when switch S is opened. As a result, the overall increase in resistance influenced by the disconnection of a parallel connection. The increase in resistance implied the decrease in current in this series connection, as stipulated by our general formula of V is equals to IR.